Welcome back. In section 3.4, we'll be looking at differential equations. That's going to be our first application of linear algebra. All right, so our goal is to use diagonalization to find the general solution to linear systems of differential equations and to quadratic differential equations. All right, so let's start with linear systems of differential equation. Definition 3.4.1 will tell us what that is. A linear system of differential equation is a system that looks like this. In unknown function, so I have n unknown function, y1, let's say y1 of t, y2 t, up to yn of t. And on that side, I have the derivative. And on this side, I have a bunch of real numbers times these matrices, where all the aij are real numbers. Okay, so if I'm looking for a particular solution to this system, it's a specific choice of function, y1 of t, y2 of t, yn of t, which satisfies all of these equations. All right, so at the start, y1 through yn are unknown functions, and a particular solution, that would be a specific choice of functions y1, t1, 2t, and so on that fit these equations. And then a general solution to this differential equation is a set of expression. So y1t, again, up to ynt. But these are not specific functions. They contain arbitrary constants, and they represent all possible particular solutions. All right, so let's look at an example that we've looked at before. If I look at the differential equation y prime equals ay, the general solution of this differential equation, we actually saw it a bit earlier. It's a constant times e to the at. All right, so a is the same a that you have in the differential equation, and then c is an arbitrary constant. Let's prove this. Now, this is actually a separable differential equation, so if you remember from Cal 2, we can solve it as follows. So I get dy over dt equals ay. I'm going to put all the y's on one side and then all the t's on the other. I'm going to integrate both sides. On the left-hand side, I'll get ln of absolute value of y, and then I'll get at plus, let's say, c1 on the right. So if I'm solving for absolute value of y, I need to cancel the log. To cancel the log, I apply the exponential on both sides. And so y itself, actually, let me write this as ec1 e to the at. And then for y, I'm going to add a plus or minus. And then this whole thing is just a constant, so I could call it c. All right, so any solution would look like this for some constant c. We actually saw something close to this. We can think of the derivative as a linear map between infinitely differentiable functions that sends f to f prime. And we already saw this. This is an eigenvector for D with eigenvalue a. And that's why we have the a here. And the eigenspace of D corresponding to the eigenvalue lambda is the set of all c e to the lambda t, where c is any real number.